Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. We will finally be talking about the first statistical property, the unbiased property. The OLS estimators are unbiased estimators of the beta null and the beta 1, and the mathematical presentation being this expectation expression that we have seen in the previous videos. As a recap, in order to get to the first statistical property, we needed certain assumptions to be fulfilled. So far, we have mentioned five assumptions: the linearity and the no perfect collinearity, proved the OLS existence. Assumption 2, the sample is random. Assumption 4, the unconditional mean of the error term is 0. We're still part of setting up the entire environment for us to be able to run an OLS. We also set a small disclaimer about assumption 2 that might not be reliable for all types of data that we have when we run an OLS, especially with time series. The most important assumption out of all of them, for which we also had a separate video indicating why do we need that on top of the fourth assumption, given that the fourth assumption turned out to be the weaker version of it. So assumption 5 is the most important assumption that will prove the unbiasedness of the OLS estimator, meaning the conditional mean of the error term is 0. So what we are saying by looking at these two expressions in here is that not in every sample, but on average, across repeated random samples. Okay. So ultimately, unbiasedness is a property of the data generation process, not the particular data set that is in front of us. And it's quite important to remember that. Now, what is the main key takeaway that this statistical property gives to us? Given this statistical property, we have what we call the key decomposition. Which means that in simple regressions, we can actually write the beta of the slope, so the beta 1 hat, as the true beta plus whatever noise that is out there, okay? So noise. Keep in mind, this is the true slope, beta 1. And this noise, we have a mathematical way of writing it, given that it's the sampling noise term. So normally we can write it as beta 1 hat equals to beta 1 plus the sum of xi minus x bar epsilon I divided by the sum of xi minus x bar squared, keeping in mind I from 1 to n in both the denominator and the numerator. So how do we actually show the unbiasedness if we are actually claiming that it's like the true slope plus some sampling noise term? Well, as any other exercise where you will be asked to show unbiasedness of something, you will have to take the expectation on both sides. So what does that mean? It's like in here, you have to put that under expectation and this entire thing under expectation. So now that we also know what the properties of the expectations are, explained in another video, we can rewrite the entire expression as the expectation of the beta 1 hat equals to the beta 1, if it is unbiased, plus, I'm going to apply now the expectation to both the numerator and the denominator, but basically we're using still the linearity of expectations in here. So I can write that as the expectation of the sum of xi minus x bar epsilon I. And then I'm just going to leave for now the bottom as is to n, 1 to n. Now that we have taken the expectations on both sides this way, let's concentrate very quickly on the nominator in this fraction. By using linearity of the expectation operator, I can rewrite that as follows. The sum of xi minus x bar, sorry, without the square, times the expectation of epsilon I. Okay, so again, this step might make it again a bit clearer why I don't have the expectation in the denominator in here, because given that that's just going to give us a number out of the expectation, it's going to be exactly that number that we have in there. So by that same principle, we're seeing this expression coming in front of the variable epsilon I in here, in this case, to which we apply the expectation. Okay, so what happens? We can apply, in this particular case, the zero conditional mean assumption. At the same time, we also have from assumption 4 that these should anyways be equal to 0, but applying a zero conditional mean plus the random sampling, so assumption 4, we have that the entire expression here is going to be 0, which means that ultimately the expectation of beta 1 hat is equal to beta 1. The same exact calculation principle can be applied to the intercept as well. For the intercept, it might be a little bit more clearer to see, because we can simply use the formula for the intercept, where we know that beta null is equal to y bar minus beta 1 hat x bar. From here, applying all over again the expectation on both sides, then we can re-express this as the expectation of the beta null hat equal to the expectation of y bar minus the expectation of beta 1 hat, and then I can just take the x bar being a number in front of this expression. Ultimately, from here, we know that the expectation of y bar is simply beta null plus beta 1 x bar. So knowing this information and substituting this, we will be left ultimately with the expectation of beta null hat simply equal to beta null. So both OLS intercept and slope coefficients are unbiased. Now, in terms of intuition, what we're saying is, again, if the error term has no pattern with x, OLS sees only the true relationship between the x and the y. Keep in mind, if we have biasness in the case, that means the error is bigger for some values of x and maybe smaller for some others. It means OLS will mistake that pattern for a real effect, and we're going to have biased estimates. In terms of like this being, the unbiasedness being the first major statistical property of OLS, you still have to be careful in terms of like what this means for you and what doesn't mean for you. Keep in mind, it will hold only when you have the linearity, random sampling, the variation in x, and between the conditional and unconditional mean, it's the zero conditional mean that's very important. Okay? We are not done yet, though, with the assumptions available, because we have to move on to proving statistical properties 2 and 3. However, these were how the first 5 assumptions form the picture or give you the idea of how we get to the unbiased property. I'll see you in the next videos for more on the OLS assumption and statistical properties.